Alright, I'm going to show you an example of how to calculate a Ka and a pKa based on the equilibrium pH of a solution and its initial concentration. Alright, so we're using HF, so let's see what we have to do first. Now we're looking for Ka, so A is for acid, so we know the HF is going to split up into H plus and something else. Now it's going to split up. If we take the H off, we'll be left with an F. But we'll not only be left with an F, it'll be F negative. And the reason for that is because the plus and the minus have to even out to give us the same charge on each side of the reaction. So we'll have neutral and neutral on each side. The other way we can do this is quite legal as well, is to include the water. Now, water is assumed here because we're dealing with aqueous solutions. But if you want to include the water, then here's how you would do it so it balanced out. HF plus H2O gives H3O plus F minus. H3O plus and H plus are considered to be interchangeable, at least as far as I'm concerned, because we are always dealing with H plus in an aqueous solution. So when you see either of these, I want you to think of them as both being equivalent. Alright, so I'll redo the equation here. And we will have initial concentrations, and then we'll have equilibrium concentrations. Both of those are in molar. The HF is going to be 0.20. We get that from the problem. The H plus and the F minus will both be 0 initially. Now after some time, the reaction will reach equilibrium, and the HF will go down by a certain amount that I'm going to call Z, and the H plus and the F minus will go up by the same amounts, Z. The reason for that is because when this breaks apart, it breaks apart into one of each. So if you had 3 of these, then you get 3 of these and 3 of these. And this would go down by 3 moles. So what's going to happen is the HF is going to go down by the same amount that the H plus and the F minus are going to go up. Now we need to see if we can find Z. Now the way we do that is we have the pH, and we know that we can, pH is 1.92, and we know that we can calculate the concentration of H plus by finding 10 to the negative pH. Now I did that in a mini lecture where I was calculating POHs, pHs, and pKas and Kas. Alright, so that gives us 10 to the negative pH. That's 10 to the negative 1.92. Now this concentration of H plus will be the equilibrium concentration, because this is the pH at equilibrium. So that gives us a value of 0.0120. Now since this is indeed the equilibrium the equilibrium concentration of H plus, you can see that Z, which is the equilibrium concentration of H plus, will give you 0.0120. So both of these end up being the same, the equilibrium concentration of H plus, and that equals Z. Alright, so now that we've got that, I'm going to erase that. And we can now calculate our Kf. Oh, sorry, our Ka. Now Ka is equal to the concentration of H plus times the concentration of F minus over the concentration of HF. We get that from our initial equation. If you had included water in your initial equation, you wouldn't include water here in your Ka expression. But it's always products over reactants. Just it's the same kind of K expression as we've been dealing with in the past. Now we know that this is equal to Z and that's equal to Z. You can see that. So that's going to be Z squared over the concentration of HF, which is 0.20 minus Z. Now once we plug in our value of Z equals 0.0120 into our equation, what we're going to end up with is this 7.7 times 10 to the negative 4, and that's our value of Ka. If I want to get the pKa, the pKa is equal to the negative log of the Ka, so I just plonk that into my calculator and I'll take the negative of the log of 7.7 times 10 to the negative 4, and that's going to give me 3.1. Alright, so that's how we find the pKa if we're given an initial solution concentration and the pH of the equilibrium solution.